Hey there, chemistry team. It's your chemistry coach coming at you with video number 12, the hopefully last one in our series on acids and bases. And we're going to get away from a lot of the math today. We're going to look at some theory and go, well, why do certain acids and bases have the Ka and Kb values that they do? So we're going to look at it based on their structure. So I want you to review on the bottom Lewis structures, review bond polarity, electronegativity, ionization, electron affinities, all that fun stuff. We're going to need to look at those values while we're doing these. So we're going to look at 3 different types. But I was going to introduce to you Pebbles, our conure. If you've never heard of a conure, I hadn't either. So say hi, Pebbles. Hello. Tweet, tweet. Yes, this house is crazy. So enjoy time with, if you got a pet, snuggle up with your pet, unless it's a porcupine or something like that. And we will get cranking on this. I'll be right back. I got to put this bird away. All right, we're going to look at a few different types of species. We're going to look at 3 different kinds of acids and only 1 kind of base in this scenario. We're going to focus more on the acids. Gets a little organic-y for me. First, we're going to look at binary acids, which I think, personally, I think these are the toughest because we've got 2 contradicting trends with these. So we'll look at the theory behind it, look at it theoretically, and then we'll look at some Lewis structures of different kinds of binary acids. Binary meaning 2 elements. It's an acid, so of course the first one's hydrogen, so it's hydrogen with another element. So HCl, HF, HBr, all the hydrohalic acids, H2S, H2TE, H2SE. So hydrogen plus 1 other element. Those are binary acids. Binary acids are just HA in general. And again, I think those are some of the tougher ones. We'll do those first, and then we'll look at the Lewis structures and some of the parameters that determine the strength of different acids. We'll be able to take, for example, the type of question you'll get is like, here's 2 acids. Based on their Lewis structures, which one would have the higher Ka value or the higher Kb value or something like that, right? Without looking at the tables. You can't look at the Ka table and just go, well, that one's higher because it's on the table. No, the point of this is to look at the molecular structure of that, the Lewis structure, and be able to tell theoretically which one has a higher Ka value or is a stronger acid. We're going to look at oxoacids. I've seen those called oxyacids as well. And those are ones where the acidic hydrogen is bound to an oxygen atom, even though we as general chemists tend to write them incorrectly because we like the acidic hydrogen out front. So things like, bromic acid, sulfuric acid, nitric acid, perchloric acid, all of those ones where the acidic hydrogen is bound to an oxygen atom on a polyatomic ion. Many, many, many different kinds of these oxoacids. But remember, that hydrogen, even though we put that out front as a general chemist to show that that's an acidic hydrogen, it's actually bound to an oxygen atom. That's what allows it to snap off there. We're going to look at the polarity of that bond and see how easy that HO bond can break off. After we do that, we're going to look at organic acids briefly. I'm not going to spend a ton of time on the organic part of things, but those are called carboxylic acids. If you've taken biology or biochemistry, you're probably familiar with carboxylic acids, where they've got a carbon with an oxygen double bond and a carbon-oxygen single bond with a hydrogen, or the COOH, the COO group, or sometimes you'll see CO2H. We'll draw those out with Lewis structures when we get to them so you can see what bonds are there and what atoms are connected to others. So acetic acid, chloroacetic acid, different formulations of that. And we'll be able to see what makes them stronger or weaker. And then we'll look briefly at organic bases, which we've covered. The weak bases are the ammonia derivatives called amines, where you just take ammonia, NH3, replace one of the, think of that as NH3, replace one of the hydrogens with some kind of organic carbon group. So you get methylamine, propylamine, so you get them all, and they're on the K. You can see a whole bunch of them on that KB table we had. Where's my KB table? So here's a whole bunch of different kinds of weak bases that are all ammonia derivatives called amines, where you've got a nitrogen with a lone pair on it, and that's like a docking station for that H plus to come in. Aniline, a whole bunch of different things. Some of them have real weird organic names to them, but I'll try to keep it as simple as possible. So we'll take a look at what causes that. But again, you need to review Lewis structures, bond polarity based on the difference in electronegativity values. So if you have an electronegativity table, pull that out, have it with you. Um, ionization energies, electron affinities, and I didn't get it on there, but bond dissociation energies as well would be important. And review the trends of atomic size on the periodic table. And you should be good with what theory is going to go into this. So let's look at the first one, binary acids. Be right back. All right, guys, let's look at part one, binary acids. And again, this is, I think, the toughest of them all. It'll get easier from this. We're going to look at this two ways. We're going to look at it theoretically, more from almost a thermodynamic, or Hess's law. Remember, Hess's law keeps lurking back when we least expect it. And then we'll look at it again in a more simplistic fashion. I actually prefer the second way, although we could actually calculate numbers doing it this way. But I just want to introduce this to you. And then for the next board, that'll be more how you can think about it like a shortcut. But theoretically, let's look at this in steps. We're taking this HA molecule, and let's look at it theoretically in the gas phase. And that's got a bond, right? Probably a single bond. We need to break that bond and create the hydrogen cation, H+, and the anion, the A-. And if we look at it theoretically from the gas phase, we could pretty much do this in 3 steps. But let's define what that value is. That's not really, we looked at bond association energies before, but that was where you just separate, you just break the bond, separate the 2 atoms, but you're not creating the ions out of it. So this is a combination of those. So we're not only breaking or severing that covalent bond, we're creating the ions. So that's really a bunch of steps in a row. You can see where Hess's law is coming from. This is called the heterolytic bond dissociation energy. So we'll use this capital D. I've seen people use capital B, capital E for bond energy as well. So D or BE. And you see the H plus A minus. That's what they mean by heterolytic. You're not only just breaking the bond, you're also creating the cation and anion in that process. We'll compare that to where we just break the bond but don't create the cation anion, which is the homolytic bond dissociation energy later. But I want you to think about this value. As that heterolytic bond dissociation energy increases, it's harder to break the bond to create the ions, which is what makes it an acid. The easier we can produce the H+, the stronger the acid and the higher the Ka. The harder it is to do that, the weaker the acid and the lower the Ka. So higher values of this heterolytic bond dissociation energy make it harder to break that, which makes it harder to produce the H+, right? It's harder to break the bond and release the H+. Therefore, the acid is weaker, has a lower Ka value. Or you can think of the other way, the lower the heterolytic bond dissociation energy, the easier it is to separate it to release that H+, which makes it a stronger acid, and the higher the Ka value. So they're inversely proportional to each other. I'm not going to have you calculate heterolytic bond dissociation energies, but I could. And you'll see in the textbook, they actually show tables of those that kind of summarizes things. Because we're going to find there's a lot of competing factors, which makes it a little confusing. This just puts them all together. Let's break this up into 3 separate factors, okay? To create that heterolytic bond association, we need to break the HA bond. This is your prototypical bond association energy we looked at back in one of the earlier chapters. And then you have bond energy tables I showed you. So we take the HA in the gas phase, just separate them. Don't create the ions though. We're just breaking the bond. That is just DHA without the charges. That is called the homolytic bond dissociation energy, or what we learned before, just the bond energy or bond dissociation energy, D or BE. Then what we got to do is take the hydrogen and remove the electron, right? So we're going to ionize the hydrogen atom. So let's take the hydrogen, remove an electron to create H+ in the gas phase. Well, by definition, if you remember one of the earlier chapters, actually back in first semester of general chemistry, that's the first ionization energy of that. Of course, it's probably not going to lose another one. That wouldn't be quite unnatural, but so that'll be just I or I sub 1. So we'll just make that I there, ionization energy. Review that from your first semester of general chemistry if you've forgotten. And then what we got to do is take that A in the gas phase and add an electron to it to create A-, which would be your conjugate base in this case. So we're taking that, adding an electron to create A-. That is the electron affinity, EA, also from that same chapter in first semester general chemistry. And again, if we're just creating a single ion, that'd be EA1. If we had to add a second one, that'd be EA2, etc. So I'm just going to get rid of that sub 1, call that the ionization and electron affinity. If I added all these together using Hess's law, you'd end up getting the heterolytic bond association energy. So really that value is a combination of the regular bond energy, the ionization energy, and electron affinity, all wrapped up in one fell swoop. So again, not going to make you do the math with this, but it's a good theoretical background to see really what constitutes how hard it is to break that bond and create the H+. Let's look at it from a simpler point of view on the next board, which is how I like to think about it. All right, here's a kind of a different way to look at it. And again, I think a little bit easier. Depends on how you think, though. There's two. When you wrap up what we talked about before with the heterolytic bond association energy, taking the three parts, the regular bond energy, the ionization energy, and the electron affinity, we can kind of wrap that up into a couple simple concepts. Bond length, right? How far apart are those two atoms? How long is that bond, stretching that electron density out and weakening it? The longer the bond, the weaker that electron density, the bond strength is, right? So it's easier to break. And so the longer the bond, the easier to break, the easier for the H+ to come off, and the stronger the acid. So as bond length increases, bond strength decreases. The longer the bond, the weaker it is. We looked at that last semester in first semester general chemistry. We talked about single bonds being longer than double bonds, being longer than triple bonds, but triple bonds having a stronger bond energy than double bonds than single bonds. So bond length and bond energy were inversely proportional. So the strength of that acid increases as the bond length increases and the bond strength decreases. So all we got to really think about is how long is that bond, which is hydrogen bound to an atom. It's a binary acid, right? So we just look at the atomic size of the non-hydrogen atom. As that non-hydrogen atom gets bigger and bigger and bigger and bigger, that bond length stretches. So I need you to review the periodic trends from your trusty periodic table. If I'm going down a column, the atoms get bigger or smaller. If I'm going across a row, the atoms get bigger or smaller. If you need to review that, pause this video and go take a look at that, because that's going to be important. The other factor would be bond polarity, right? This deals with the aspect of creating the H+ and the A-, right? Or the breaking that electron density and having it go to the A-. Remember, we looked at that last semester as the change or the difference in the electronegativity value between the two atoms of the bond. You got the hydrogen and the non-hydrogen, like a chlorine or bromine. You can look up the electronegativity of one, the electronegativity of the other, and then subtract those and get the delta EM. The higher that value, the more polar that bond, and the easier it is when it breaks apart to form the H+ and the A-. So the greater the electronegativity difference between these, or in essence, the greater the electronegativity of the non-hydrogen atom, because it will always have hydrogen, so it really is based on the other atom. The higher the electronegativity of the other atom, the easier it is to release that H+, and the stronger the acid, or the higher the Ka. Now, if you're going across a row or down a column, we've got a problem. We're going to find out that these factors compete with each other. They counteract, right? So if I'm going down this column, size is increasing, right? So if I take a column here and I go down, the size of the atoms are getting bigger and bigger and bigger, which means the bond length is increasing as I go down, which means the acid strength increases going down based on bond length. But if you remember, electronegativity decreases going down. Oh no, which means the delta En gets smaller going down and the acids get weaker. So based on the polarity, bond polarity, they get weaker going down. Based on the bond length, they get stronger going down. They're opposites. Oh man, how are we supposed to think about this? Same thing going across, right? When you go across, atom size is getting smaller, right? So the bond length is decreasing. So the acids should be getting weaker as you go across, but as you go across, the electronegativity is going up. So it's more of a polar bond, so it should make it a stronger acid. So it's stronger polarity-wise, but weaker bond length-wise. Again, they compete, they counteract. How are we supposed to figure this out? So when we look at going across, we have to treat them separate. Going down a column, binary acids going down a column, or binary acids going across a row. We're going to have to look at these factors separately and go, which one dominates? Does the bond length, is that the dominant factor? Or is the bond polarity the dominant factor? And once we determine that, then we can find the trend for that. It simplifies it, but the heterolytic bond association energy has it all wrapped in there. So let's talk about those two factors, that what's dominant going down versus dominant going across. All right, here's how you attack it if you're going down the periodic table, going down. So you're looking at like hydrohalic acids, HF, HCl, HBr, or you could look at H2O, H2S, H2SE, H2TE. Just going down, looking at the binary acids going down a column. Remember this, the dominant factor is the bond length. As you're going down, those atoms are getting bigger and bigger and bigger. You're adding electron shells. Yes, the electronegativity is changing, but not as dramatically as the atomic size. So the atomic size dominates. Bond length is the dominant factor. Just ignore the bond polarity and the electronegativities. This will be your dominant factor. So for example, if I take the hydrohalic acids, going from HF to HCl to HBr to HI, atom size gets bigger going down, right? So you have the smallest atom here, the fluorine, getting bigger, 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 and the iodine atom's the biggest, which means we have increasing bond length going down the column from HF to HI, right? If the bond length is increasing, that means it's a weaker bond. It's easier to break. So that would make this the weakest acid on top. And as you go down the periodic table, they get stronger and stronger. So HI would be the strongest acid of that bunch. And I actually put Ka values here. So HF is a 6.6 times 10 minus 4 for its Ka, which is a typical weak acid. The other three are strong acids. But we can get actual Ka value. In water, they're all pretty equivalent. So to get the specific values, you have to do them out of water. But HCl is 1 times 10 to the 6th, HBr 1 times 10 to the 8th, and HI is 1 times 10 to the 9th. So you can see that trend. So remember, going down, it's bond length that dominates. You'll see when we go across, it'll be the opposite. All right, if we are going across a row or a period here, so we're looking across this way. So for example, if I'm comparing, H3S to H2SE to HBr, or pH3 to H2S to HCl, just going across. The atom size goes down, but not a lot. But the electronegativity value changes dramatically. All right, so going across a column, again, changes in sizes isn't huge. Going down, it is huge. But so going across, by far, the bond polarity is going to dominate. All right. So as the electronegativity of the non-hydrogen atom increases, the bond polarity increases, creates that separation of charge within that bond. It's easier to get the H plus A minus. That makes it a stronger acid, all right? For example, let's take H2S versus HCl. So we've got H2S here going across to HCl. Just looking at those two to focus, we could go all the way across the row if we wanted to. So the electronegativity value, so if you have your electronegativity table, you can just look up these values. So you can see sulfur is a 2.58 there. You can see the chlorine is a 3.16. Depending which table you use, some of them go to 1 decimal, some of them go to 2, doesn't matter. But the electronegativity of sulfur is a 2.58. The electronegativity of chlorine is a 3.16. So the chlorine's a lot more electronegative, which is going to make those electrons less shared, right? It's more polarizable. So the difference in electronegativity is 0.38. If you take hydrogen as 2.2, you're good to 1 decimal. For HCl, it would be 0.96. So the difference in electronegativity is huge for HCl versus H2S, that HS bond, which means the HS bond is less polar. The HCl bond is way more polar, making H2S a weaker acid and HCl a stronger acid. So you go across left to right, acid strength increases. If you go down, right? So it increases going across and it increases going down. So you can kind of follow that trend. But again, going across is the electronegativity factor, the bond polarity. Going down, it's the bond length of the size. So H2S has a Ka of 1.0 times 10 minus 7. Hydrochloric acid is a strong acid at 1 times 10 to the 6. Huge difference. So that's it. That's how you do binary acids. Let's take a look at oxoacids, which I think are a little bit easier. All right, here we go. Remember, we're looking at 4 different things: binary acids, oxoacids, organic or carboxylic acids, and organic bases or amines. Hardest one's done. Oxoacids. Only 2 factors to worry about for this one. So again, that's where the hydrogen is bound to an oxygen atom on a polyatomic ion. That's why it's oxo or sometimes oxyacids. The main overall gist of this is, as the electron density, you've got this OH bond, right? The hydrogen's bonded to an oxygen atom. As electron density is pulled away from that bond, it polarizes it and weakens it, makes it easier to pop off. So as electron density is pulled away from that bond, the bond polarizes and weakens, makes it easier to ionize, and increases the acid strength. So we have to look at the factors that pull electron density away from that. It's going to get a little more organic here. Here's the 2 factors. The number of terminal oxygen atoms. So we have to draw the Lewis structure, and I'll show you what a terminal oxygen atom is, because oxygen's very highly electronegative, like number 2, second only to fluorine. So that pulls electrons. And then the electronegativity of the central atom. That's the atom that the OH bond is connected to. Is that a bromine? Is that a chlorine? Is that a sulfur? What is that? The more electronegative that is, the more it's going to pull electrons away. So let's look at each of those 2 factors in turn, and we'll be done with this. Let's take a look at the first factor, the number of terminal oxygen atoms, and then we'll look at the electronegativity of the central atom. So this will be the dominant factor. Always look for the number of terminal oxygens first. If they're the same, then go to the next one, look at the electronegativity of the central atom. But if they're different, this is all you really have to worry about. So in this situation, the central atom is chlorine across the board. So that's equal across the board. So let's take a look at these. As the number of terminal oxygen atoms increases, the OH bond weakens and the acid strength increases. All right? You can answer these without understanding it, but I want you to understand it. Let's take a look at the Lewis structures. Let's take a look at perchloric acid versus chloric acid versus chlorous acid versus hypochlorous acid. Look at the Lewis structures, right? You got the chlorine as the central atom surrounded by the oxygens, and the hydrogen's bound to the oxygen, right? That doesn't show that in the molecular formula, but the hydrogen's bound to the oxygen. That's why it's called an oxoacid. Do you see that these oxygens here, here, and here? Let me circle them. I'll do it in green. That one there, and that one there has 3 terminal oxygen atoms. That is 3. This one, oh, I did too many. That would have been the same molecule, right? So now we got HClO3. That's not a terminal oxygen, right? It doesn't end with oxygen. So HClO3 has 2 terminal oxygen atoms. HClO2 has 1 terminal oxygen atom. And HClO has 0 terminal oxygen atoms. Okay. As you have more terminal oxygen atoms, that's pulling electron density away, right? You can see that's pulling electron density away from the OH bond. And the more you have, the more those highly electronegative terminal oxygens are weakening this OH bond right here. So it's weakening the OH bond. Pretty easy to think about. Just draw gotta have the Lewis structure, but look at the number of terminal oxygen atoms, and the biggest one wins. I popped in the Ka values. Not that you need the Ka values, but it kind of proves it. We know perchloric acid is a strong acid. Very, very large Ka. I don't even know what it is. Way bigger than 1, right? The chloric acid is about 500. So a lot of people, some professors treat that as a strong acid. It's not characteristically put as a strong acid, but some people argue for that. Chlorous acid is a weak acid at 0.011, still pretty hefty. And then the hypochlorous acid is a wimpy 2.9 times 10 minus 8. So it has a huge factor. As you increase the number of terminal oxygen atoms, it dramatically increases the acid strength. All right, the second part for oxoacids is the electronegativity of the central atom. But I want you to think about this is only if they have the same number of terminal oxygen atoms. That's going to be the dominant factor. Look for that first. But if they have the same number of terminal oxygen atoms, look at the central atom, right? The non-oxygen, non-hydrogen atom, by the way. As the electronegativity of that central atom goes up, it pulls the electrons away, right? It's pulling electrons away from this OH bond here, and it's weakening that OH bond. It's polarizing it, which makes that easier, makes that hydrogen easier to pop off and a stronger acid. So as the electronegativity of the central atom goes up, it's a stronger acid. So you can compare, say, chloric versus iodic acids, right? I got 2 terminal oxygen atoms on this one, 2 terminal oxygen atoms on that one. So they both have 2 terminal oxygen atoms, so we don't have to worry about that factor. If those were different, we'd be done. So let's look at the next factor, the next level. What's the electronegativity on chlorine? 3.16. What's the electronegativity on the iodine? 2.66. So you just look on your trusty electronegativity table here, and you can see, right, chlorine's a 3.16 there, iodine's a 2.66 there. Have your electronegativity table always ready for you with you. Since that's a higher electronegativity, it polarizes that OH bond more. This is a stronger acid with a Ka of about 500. This is a lower electronegativity, so that's the weaker acid, Ka of about 0.16. They're both pretty big, but that's dramatically bigger, much stronger acid because the electronegativity is higher. I think these are much easier than binary acids. All right, let's take just a quick little couple-minute intro into organic acids and bases. And we're done with chapter 16. Boom! All right, brief little introduction into organic, you'll see. But if you do the Lewis structures, you can do it. So we're going to be looking specifically at carboxylic acids, which technically are oxoacids. The hydrogen, the acidic hydrogen, is bound to an oxygen. But this is the functional group in organic chemistry, the COOH or the COO group, sometimes CO2H. And then this R just stands for the rest of the molecule, some organic carbon-based group, unless it was just H, right? What we're looking at is how on this part here, this R part, is there something that can pull electrons away from this OH group and polarize and weaken that bond? So the stronger the electron withdrawing groups and the closer, because this could be a long chain here, the closer they are to this bond and the more electron withdrawing, i.e. the more electronegative they are, the weaker this bond is and the easier that hydrogen is to pop off and the stronger the acid, right? The higher the Ka value. So what I'll do is put up some examples just so you can see how it works out. It's not too bad. You just you have to be able to draw Lewis structures. If you get the Lewis structure wrong, you're toast, man, or as they say in Minnesota, toast. Are you ready for a little organic weirdness here? Okay, here's 4 different carboxylic acids. All right, so we've got 4. Now, they look a little worse than they are, but as long as you do the Lewis structure, okay, you can see the carboxylic acid, the carboxylate group, right, on all of them. So this is the R group here that's different for each one. That's all that matters. And we're looking to see what weakens this OH bond right there. What's weakening that bond? So we're looking at the ability to pull electron density away from that bond. All right, so we've got the acetic acid right here, 3-chloropropanoic acid right here, bromoacetic acid, and chloroacetic acid. Now, I wrote the Ka values down, so you can see the 1.8 times 10 minus 5, the 1.0 times 10 minus 4, 1.3 times 10 minus 3, and 1.4 times 10 minus 3. So we're getting stronger going across. So this is my weakest acid. Let's talk about why. And going across this way, this is my strongest acid. Remember, 2 factors. How close is the electron withdrawing group to the OH bond, and how electronegative is it? How strong of a withdrawing group? So notice here, acetic acid just has a CH3 group, right? There's no highly electronegative atoms, nothing like that. So that's kind of your baseline, 1.8 times 10 minus 5. Now let's look at a situation where we add this ethyl group, but we got a chlorine. So 1, 2, 3, 3-chloropropanoic acid. You don't know how to name that in this class. But you see the chlorine group? That chlorine is going to be pulling electron density away from that hydrogen. So it weakens that bond and makes it a stronger acid. Not a lot stronger because that chlorine's pretty far away, right? It's a couple carbons away. Let's look at bromoacetic acid and chloroacetic acid. These both have 2 carbons, but notice this one is a bromine on that carbon and a chlorine on this one. Right? So if we compare these two, they're exactly the same in the positioning, the second carbon, but bromine has electronegativity of 2.96, chlorine has electronegativity of 3.16. So they're the same distance away, right? 2 carbon atoms away. But chlorine's more electronegative, so it has a slightly higher Ka value of 1.4 times -3 versus the bromine one, the bromoacetic, with 1.3 times 10⁻3. So that looks like the dominant factor is more how far away it is, but it's pretty tight. And if you can control the 3-chloropropanoic acid to the chloroacetic, see the chlorine's on the second carbon here, it's on the third carbon there. So it's further away, so that makes that a weaker acid than this one. And if you look at these two, even though these are different atoms, the chlorine's more electronegative than the bromine, but the chlorine's further away in the 3-chloropropanoic acid than the bromine is in the bromoacetic acid. So even though that bromine's less electronegative, it's closer and is having more of a factor. So look for closeness first, and then look at the electronegativity second. So if they're the same distance away, look at electronegativity. If not, look at how far away they are. Pretty straightforward. Let's do about 1 minute on organic bases and we're done. All right, let's polish this chapter off with organic weak bases or amines. And we've looked extensively at these on our KB tables. We just haven't looked at the theory behind them. So here's a general form for an organic amine. See the nitrogen with the lone pair. See the hydrogens, and you've got this R group, some organic group. Now you could replace these hydrogens also. You could have R and R prime and R double prime. So we could replace any 1, 2, or 3 of those hydrogens with carbon-based groups. And that lone pair is where the hydrogen ion comes in, connects, and forms that conjugate acid. Right? The more electron withdrawing this R group is, right? It's pulling, so the more that it pulls electrons away, so the more electronegative that group is, whatever's in there, maybe a chlorine atom or fluorine atom in there, it's pulling electron density away from that, right? That makes it a weaker base. The more the electrons are pulled away from here, the less likely, the more attracted the H plus is to it. So the more electron withdrawing this group is, that R group, the weaker the base is, the lower its Kb. It's less likely for the hydrogen H plus to connect to it. It wants a high electron density there. So let me drop a few examples and we'll be done. Here's some ammonia derivatives for you called amines. And I have ammonia up here. So flat ammonia, kind of our baseline, has a Kb value of 1.8 times 10⁻5. You can see on that table. So let's look at, so we're going weaker this way and stronger this way. I put the Kb values. So let's look at what happens when we replace a hydrogen with an electronegativity value of 2.2 with a bromine. Now bromine, not super electronegative, but bromine's a 2.96, right? That's more than a 2.2. So this is a 2.96. So that nitrogen obviously is more electronegative than most. So that nitrogen's pulling electrons away from that hydrogen, right? But it's not quite as easy with the bromine. So it's got less electron density on the nitrogen, which makes this a weaker acid. So it's less likely for a hydrogen to attach because you've got a more electronegative species here than the hydrogen pulling that back. Now let's go the other direction, where now we're adding some organic groups. Like here we have a methylamine, a methyl group. Here we have 2 methyl groups, dimethylamine. And you can see the Kb for ammonia is 1.8 times 10⁻5. When you put the bromine on it, it drops it dramatically to a 2.5 times 10⁻8. That's much weaker. When you put the methyl group instead of a hydrogen, it gets 4.2 times 10⁻4. So it's a higher Kb. It's a stronger base, still pretty wimpy, but not by a whole lot. So what's happening here, as you put these organic groups on there, that nitrogen is pulling more electron density towards itself from those organic groups. And the more carbon groups you put there, or the larger that carbon group is, the more electron density that nitrogen is going to have, and the higher the Kb value, and the stronger the base. So you can see with one methyl group, it goes to 4.2 times 10 minus 4. With two methyl groups, it goes to a 5.9 times 10 minus 4. Not a huge difference, but a measurable increase in the base strength. They're all weak bases, but you can actually see the differences between them. So you can see those Ka and Kb values on the tables are different because of those structures. That's it for chapter 16, guys. Yeah!